Hey everyone, in this video we're going to talk about gears in general and specifically gear train examples as well as types of these gear trains such as a compound reverted gear train. This video is part of a lecture series on mechanical design too, so let's dive into this first example problem that we see on our page. So we're given an example and it's not really a problem, it just tells us what we have, but essentially we are trying to design this gearbox that provides an exact 30-to-1 increase in speed. And what we mean by speed is obviously rotational speed. And the other things is we know that we need to create a gearbox for this. And we have a few parameters that we can take into account as we do this. And we're going to do this example problem learning a few things in theory as well. So just stick with me when we do some theory as we're learning the system. Now, two of the criteria that are given is the questions that are given is to minimize the size of the gearbox. So we need to try and make it as small as possible. And making it as small as possible just means basically minimizing the number of teeth or minimizing the diameters of everything. And then the other thing is what are the tooth numbers? So we're going to try and find out what the tooth numbers are for the system. Now we can create the system in however many ways we want. And we know that we need to provide an increase in speed. So if we need to create an increase in speed, and this is where you can already pause the video if you want to, think about whether or not we're going to have a small gear to a big gear or a big gear to a small gear in order to increase the speed. So I'll let you pause it here and then you can resume. So essentially, if we want to increase the speed, we usually want to go from a large diameter to a small diameter. So your first instinct from previous lectures would be, okay, let's just look at how we can increase the speed by a ratio of 30-to-1, or essentially a train value of 30-to-1. Well, one way to do this is to say, all right, let's draw a gear that's number 2, and then a small gear connected to it that would be number 3. Again, remember that number 1 is the frame of reference, so we always start with gear 2, and then gear 3 would be the next gear in line, essentially. So let's say we have gear 2 and 3 drawn like this, and they're in contact right here. And what I drew was basically only their pitch circles. Okay, so I draw a simplified diagram of them. Now, can we actually do this? So can we actually increase the rotational speed of 2? Let's say 2 is going clockwise, 3 is going counterclockwise, omega 3. Can we, or we can also write lowercase n2 and n3, can we actually increase the speed by 30? Well, the answer would be theoretically yes, but practically this is not actually done because it creates a lot of problems in terms of interference and tooth design. You would need a lot of teeth on gear 2 in order to transfer 30-to-1. So one rule of thumb and one rule of design that the designers have put in place, and I'll write the rules on the right side, so this is kind of like theory. The train value, which is essentially the increase or reduction. So if the train value is 10-to-1 or less, so meaning we need to increase or decrease the speed by 10 or by a factor of 10 or less, we can use one pair of gears. If it is anywhere from 100-to-1 all the way to 10-to-1, so in that range of 101 to 10-to-1, we want to use a 2-stage gear train. Okay, and this is going to be called a compound gear train. So if you think about it, if you have two 10-to-1s in series or two 10-to-1s attached together, you would essentially get a ratio of 100-to-1. So that's the reason why we would use a 2-stage gear train. So looking at our problem, now that we have this new theory in place, since our train value, so we can say that E is going to be equal to 30. Since our train value is going to be equal to 30, we can say with certainty that we need a 2-stage gear train based on the rules above. So now we can start designing a two-stage gear train. And what I'm going to do is I'm going to cross out this one because was a good idea, but we actually can't put it in place because of the rules on the right side. Okay, so let's start thinking about how our value essentially works. Okay, so let's think a little bit about how. So remember, we have the equation n last is equal to e times n first. Okay, so we have n last, the last gear, is equal to e times n first. So we know that in this case, we want given in the question, we want an exact 30-to-1 increase in speed. So that means that the speed for n last is going to be 30 times, so I'll put it in brackets because it's not the actual value, is going to be 30 times the n first. So e is essentially equal to 30, okay? That's how we find our train value. That's our train value or our increase in value that we want. So we're going to need a two-stage compound gear train. So in order to design a two-stage compound gear train, I'm going to design it here at the bottom, and you'll see how I design it, but you should be able to learn how to design these by yourself. So depending if you have a speed reducer or a speed increaser, you're going to have different gears, but essentially what we're going to do is we're going to create two stages. So we're going to create one stage here. So this is going to be stage one, and I'm going to put the axles just as straight lines in the middle. And I'm going to call this gear 2, gear 3. And again, gear 2 to gear 3, gear 2 is going to have a larger diameter than gear 3 because we're trying to increase the speed. So that's going to be the first step. Now, the next step is to connect 3 to another stage called stage 2. So I'm going to connect this with another gear with a wide diameter again, and then I'm going to connect that with a small diameter gear and create another axle here. So we have gear number 4 and gear number 5. So very similar to our example from last lectures, we see that we have two stages here, and those two stages are kind of offset from each other, and they're connected through an axle in the middle. So I'm just going to highlight really quick in blue. We have stage 1 here, and we have stage 2 here. And these two are connected by an axle in the middle. Now, the next thing we need to figure out is we know we have a train value of 30. Okay, so we know that we need to increase the speed by 30. So how are we going to increase the speed by 30 if we need to do it in two stages? So if we think about it, let's say we increase the speed by, let's say in the first stage, we increase the speed by 2. Okay, so let's say gear number 2 is rotating at an assumed 1000 RPM, and then we get to gear number 3, and now it rotates at 2000 RPM. So let's say we went up by 2. Then what would 4 to 5 need to do? So 4 would be rotating at the same speed as 3, so it would be going at 2000 RPM, and then we would need that to go all the way to 30,000 RPM to get our train value of 30 to 1. So that means that we would need to increase the speed 15 times from 4 to 5. So there's different combinations in which we can split our 30 into different pieces. So one thing that comes to mind immediately is to try and use whole numbers. So what we're going to do is we're going to try and find all the factors from our for our e. So we can say that 30 can be, so if we need to do it in two parts, if we need to get to 30 in two parts, one way we can do it is say, let's do the square root of 30. If we do the square root of 30, that means we would have to increase by 5.47 on stage 1 and 5.47 on stage 2 the speed. And that would give us a speed of 30 at the end. Now, this is unrealistic because we actually can't get that done. It's very difficult for us to get that done. And the number of teeth have to be a whole number. They can't be like, we can't have 14.2 teeth, for example. We need to have whole numbers in terms of teeth. So very, very difficult to increase a value by the square root directly, except if the square root works out. If you had an e of 36, you could do 6 times 6, and that would work really well. So what we're going to do is we're going to actually list all of the different e's that combine to make 30. So one of them is 5 times 6, the closest to 5.47. Then we have another one that's 10 times 3. Another one is 15 times 2. And using all whole numbers. And the last one is 30 times 1. So now, because of our rule above here on the right-hand side, we can already take out 2 of these and say we can take out these 2. These 2 are not going to work because we have a train value on one specific stage that would be higher than 10. So 15, if we increase by 15 in one stage, that wouldn't work. We would have to break it down into 2 stages. If we increase by 30 in one stage, that basically defeats the purpose, so we wouldn't do that. So the only 2 options that we have available are 10 by 3 and 5 by 6. Now, you could use 10 by 3 or 5 by 6 equally well. There's no restrictions into you using 5 by 6 or 10 by 3. You could use both. Now, we are going to choose 5 by 6 because in the question, we were told that we had to minimize size. So this is related to a decision to minimize size. So now that we've chosen 5 by 6, we can start coming up with a model for our teeth number that we would need in order to increase the speed by 30. So we're going to make this model as simple as possible to start with and then figure out a number of teeth that could work together. So first things first, we know that we have 4 sets of teeth that are going to be connected together. So we have N2, N3, N4, and N5. Those are all our gears. We know that N3 and N2 are connected together, and N4 and N5 are basically connected together as well. And one thing we know about gears being connected together is that they need to have a constant diametral pitch or if using SI units module. So we need to satisfy that requirement for both sets. Now, both sets can have different diametral pitches and different modules, but within each teeth, they have to have the same. The reason why they're separate is because 3 and 4 are connected by an axle, so they're actually not connected by teeth, so they could be different if needed. Okay, and we also know that 3 and 4 have the same rotational speed. Okay, so 3 transfers the rotational speed through the axis to 4. Okay, so what are some of the numbers that we're going to put together to, what are some of the numbers that we're going to put together for N2, N3, N4, and 5? So since we know that the train value has to be 6 by 5, we can decide, well, either to use 6 or 5 for either train. So we could say like the 2 and 3 train could have an increase of speed of 6, and then the 4 and 5 train could have an increase in speed of 5. It's really up to us. It doesn't really make a difference in terms of the change, but usually, as a rule of thumb, we usually make the biggest train value jump or the biggest gear increase or speed increase on the first gear that's connected. So what we're going to say is that N2 is going to be equal to 6, N3 is going to be equal to 1, and then N4 is going to be equal to 5, and N5 is going to be equal to 1. So by doing that, what we're saying is that with N2 to N3, we're going to increase the speed 6 times. And then when N4 to N5, we're going to increase the speed 5 times. And in total, that's going to increase our speed 30 times. And if you actually go through the math, it would work. Now, these number of teeth that we put in are obviously completely incorrect. Okay, we can't have we could potentially have a 1-tooth gear with a 6-tooth gear, but that seems a little bit unrealistic, okay? And it's unrealistic because we actually know that we would probably get interference if that were the case, okay? And a 1-tooth gear is actually very unrealistic. But mathematically, if we didn't have any problems with interference, we could theoretically go with 6 and 1 and 5 and 1 and get away with it completely fine. So what we need to do is we need to decide, okay, we clearly probably cannot have 6 and 1 tooth and 5 and 1 tooth. And we know that in order to design a gear train, or a gear mesh, let's say, not even a gear train, to design a gear mesh, we need to always satisfy interference. This is our job as good engineers, essentially, because we want to design systems that do not have interference, because then they will probably wear out and break. So what we need to do is we need to figure out what the interference number is, or what the number of teeth on the pinion as a minimum are. So we need to find the minimum number of teeth for the pinion based on our gear ratio and based on some parameters that we come up with. Now, obviously, in order to solve for our problem, we're going to have to solve for it with some assumptions that we're going to have to make. So one assumption that we're going to make is that the angle of line of action will be 20 degrees. Okay, so that's the pressure angle of our gear is going to be 20 degrees. We could have chosen 25 or 14.5, but we're going to choose 20. We're going to assume that we have full teeth with K is equal to 1. And we're going to have an mg of 6 and an mg of 5 for each of the gear trains. So there's going to be two different gear ratios. One is going to be 6 and one is going to be 5. Okay, remember that mg is always the number of gear over the number of pinion. So for one stage, it's going to be 6, and for the other stage, it's going to be 5. Now, once we do that, we're able to calculate a number, and we can calculate the number for mg equals 5 and mg equals 6, and the values are a little bit higher than 15 for both. So they're going to have different values, but the values are so close together between mg 5 and 6 that essentially our NP is going to be required to be 16 for both. Okay, and you can do the math yourself. You have the equation in your formula sheet available. So you can do the math yourself for NP with an mg of 6 and an mg of 5, and you'll notice that the minimum value is 16 for both. So that means that if we go back to our gear teeth number, we need to have the NP at least equal to 16. Now, in our system, the pinions are these two values. So I'll just highlight that the pinions are these two, N sub P, N sub P. Those are the two pinions because they're the smaller gear out of the two in the connection. So we need these NPs to be at least 16. But we also need to minimize the size of the gearbox. So if we need to minimize the size of the gearbox and satisfy all the requirements, what we can do is we can essentially take these numbers. So I'm going to just write them back out. So N2 is equal to 6, N3 is equal to 1, N4 is equal to 5, N5 is equal to 1. What we're going to do is, in order to get everything and keep the ratios the same, what we're going to do is we're going to multiply this by 6. And we're going to multiply by 16, not by 6. So we're going to multiply by 16 so that we can get at least 16 teeth in N2, N3, N4, N5. So our value, if we multiply by 16, would be equal to, and I'll just draw some arrows to get there. So we'll have N2 is going to be equal to 6 times 16, which is equal to 96. N3 is going to be equal to 16. N4 is going to be equal to 5 times 16, which is going to be equal to 80 teeth. And N5 is going to be equal to 16. So what we've determined is the number of teeth, and we can add a T at the end to just say teeth if we want to. What we've determined is that if we need to design a 30 to one speed increaser, we need to use a two-stage gear train, compounded gear train, and the number of teeth would have to be 16 on the pinions, which are N3 and N5, and therefore the number of teeth on N2 and N4 would have to be 96 and 80. And N2 and N4 could actually be flipped around if you wanted to. So you could have, as a convention, you could also have that N2 would be equal to 80 and N4 would be equal to 96. But that really depends on how you design your system and how you come up with your solution for your systems. But typically, as engineers, we always, if we have two different ratios of increase to get to a value, we usually use our first gear to do the biggest increase. So 96 over 16 is a bigger increase in speed than 80 over 16. So we do the first step is usually the bigger increase. Okay, so that concludes this example problem. Now, a few more things about gear trains, and then in the next lecture, we'll talk about some more example problems. So first things first is, what if we had a speed reducer? So a speed increaser has a speed increaser before had a speed of 30 to 1. Okay, so we said when we increase, we have a ratio of 30 to 1. Okay, we're increasing 30 to 1. Now, a speed reducer has a 1 to 30 ratio. So what we're saying is we're dividing the speed by 30. So now our train value, instead of being 30, our train value would be equal to 1 over 30. Okay, and if we were to design a speed reducer in the same way as we did before, what we would say is, well, we would divide this by 1 times 5 times 6, 1 over 5 times 6. Okay, and then we could do the exact same thing, except gear 5 essentially would be our gear 1, our gear number 2, gear 4 would be our gear number 3, and we would flip the system around. So a speed reducer is just the inverse of a speed increaser. So it's very, very similar. The only thing is that the train value is usually written as 1 over 30 instead of 30, but the math is pretty much exactly the same. Now your mg does not change, okay? So your m sub g, or your gear ratio, is always ng over np. So that value would always be 5 or 6, because you're always putting the gear on top over the pinion, okay? So just a little bit of a point here, that when you're doing problems, if you're asked to find the train value, if you have a speed reducer, the train value would be 1 over the amount that you're reducing by, okay, instead of just the number outright. But again, it'll be clear once you do some example problems as well. Okay, so the next thing we want to talk about is a specific case of a compound gear train, which is called the compound reverted gear train. Okay, so we're going to talk about the compound reverted gear train. And what a compound reverted gear train is instead of having a system how we drew it before with, for example, 2 to 3, so let's draw them really quick, 2 to 3, and then we connect 3 and 4 together, and then we connect a fifth gear here at the bottom. Instead of having this type of system, what we can do is we can actually move this gear up to here and place it at the top. And what we can do by placing it at the top is actually minimize the size of our system even more by allowing to have it as a gear that's in line with axle number 2. Now, it's not actually going to be part of axis number 2, so the axles are going to be separate, so they're not going to be connected here. Okay, so there's no connection here, but they're going to be in line with each other. And the compound reverted gear train, the big advantage of it is that it basically saves the maximum space possible in terms of your system. So let's look at the system a little bit really quick, and let's figure out how we can actually design the system. So there's one extra condition that we have to add in order to make a compound reverted gear train, because geometrically, we now have to have the same distance here as the distance here. So that means that we need to somehow constrain it a little bit, because before we didn't have that constraint. Before, our gear 5 would just be at the bottom and it could be whatever size and it didn't really matter where it was. Okay, so let me redraw just a compound reverted gear train as a whole and have it redrawn so that we can look at it a little bit more in detail. So let's say we have gear number 2, and I'm going to make it a little bit bigger just so we have access to it. Then we're going to have our axle through the middle. Let me redraw that axle a little bit more central. Okay, then we have our gear number 3 with our axle in the middle. And what I'm going to do is I'm going to start drawing a dotted line between 2 and the next one. And then here, I'm going to have a solid line because we know the axle is connected. I'm going to have gear 4 here. And then I'm going to have gear 5 placed here on the same place. And then I'm going to add an axle here. And I'm going to make a point of stopping the axles on this side. And at the bottom, the axle is a whole axle between the 2 gears. Okay, so we have gear number 3, gear number 4, and gear number 5. And we can see that now, number 2 and 5, 2 and 5, 2 and 5 are in line. Okay, so if they're in line, then that means we can start putting some numbers to it and we can start analyzing the system. So let's add, for all these gears, let's add the diameters on our diagram. So we have diameter 2, diameter 3, diameter 4, and diameter 5. And the reason why we're writing the diameters is because we have to create a constraint, or we have to create an equation that will constrain that essentially the distance from here to here has to be equal to the distance from here to here all the way along. So the distance between 2 and 4, or the axles between 2 and 4, and the axles between 5 and 4, and the axles between 2 and 3 have to be the same throughout. So what we can say is we can come up with an equation for this. So let's come up with an equation for the distance between here and here. Okay, so let's come up with an equation for the distance between here and here. So if we look at the left side of our diagram, we can say that d2 over 2, okay, so half the diameter, so from the center of 2 to the edge of 2, we have d2 over 2 plus d3 over 2 can be equal, so that's the value on the left side, can be equal to the right side, which is going to include d5 and d4. So we're going to have d4 over 2 plus d5 over 2. Okay, so that's going to be a condition. Now, the other condition that we need to have is, in order to design a compound reverted gear train, we need to have our diametral pitch, or capital P, is going to be the same for all gears. So we're not going to design now with just capital B being the same between 2 and 3 and 4 and 5 independently. They're all going to be the same. In order to be able to design this type of system, you need to make them all the same. This is kind of a rule, okay? You can't escape that rule, okay? And then what we can say is, well, we know the equation for P is N over D. So number of teeth over diameter. So then we can rearrange and we can plug into the top equation. We can say D is equal to N over P, okay? And what we can do is we can plug it into this equation. So D is equal to N over P is going to be plugged into this equation. So we're going to write that N2 over 2P2 plus N3 over 2P3 is equal to N4 over 2P4 plus N5 over 2P5. Okay, so we just rewrote the equation in terms of diameter as a function of number of teeth and diametral pitch. Now, since we said that P is the same for all gears, that means that P2 is equal to P3 is equal to P4 is equal to P5. So if we look at the equation above, we can say that all the P's are essentially going to cancel in this equation. We can also multiply the whole equation by 2 and get rid of the 2's. So we can get rid of all the P's and all the 2's. And we're left with an equation that's very elegant that says that N2 plus N3 is equal to N4 plus N5. Okay? And this equation is valid for, or it's called a condition that needs to be working for a compound reverted design. Okay, it needs to be satisfied for a compound reverted design. So now what we can do is we could say, let's take our example problem from before and say that we would want to minimize the size, and we would have E is equal to 30. So we could take our original example and say E is equal to 30. We need to minimize the size. Okay, so E is equal to 30. We need to minimize the size. We know that we need a speed increaser, so increase speed. Thirty times. And we're told we have to use a compound reverted gear train. And so if we did that, we know that to minimize the size, we would use an E of 5 times 6 or 6 times 5. Okay, and we already know that NP minimum is equal to 16 for both. The mg is equal to 5, so I'll put for m sub g is equal to 6 and m sub g is equal to 5. So we already know that. And then we had 4 unknowns, which were n2, n3, n4, and n5. And in the previous example, we came up with 96, 16, 80, 16, and that would satisfy our MGs. Now, the problem here is that if you were to design this system or our previous solution as a compound reverted gear train, you would also need to satisfy N2 plus N3 is equal to N4 plus N5. Now, is this satisfied? We can clearly see that N2 plus N3 and N4 plus N5 is not satisfied. So we can say that this is not satisfied. So a design we came up with last time, which was not a compound reverted gear train, it was just a compound gear train, would not satisfy the design requirements of having all the axles together. So let me just draw it really quick. So if we had 2, 3, so this is 2 at the top, 3 in the middle, then 3 and 4 would be connected together, 4 would be a big gear, and then 5 would be a small gear. We would not be able to satisfy it through our solution before. So what we need to do is we need to come up with another solution. And what we'll do is we'll stop this video here. And in the next video in the series, we're going to be solving this problem, trying to solve this problem to figure out how many teeth we would need to satisfy this n2 plus n3 is equal to n4 plus n5. Obviously, one way to do it is to try trial and error with the MGs, but there is a way, there is a technique to be able to do it, to solve it faster than trial and error. So we'll do that next time.